Swayam Prabha. Digital India. Educated India.
Welcome to lecture 30 of Mechanics of Materials. In the last lecture, we saw how to analyze members subjected to twisting moment or torsion. In today's lecture, we will see a different boundary value problem wherein you have an annular cylinder which is inflated from inside held at a constant length. Okay. So, what I have is I have this annular cylinder. I am holding it fixed, okay, and then I am inflating it from inside. And I am inflating it from inside like this. Okay, and I am interested in analyzing this structure for stresses and displacement. Okay. Since the geometry of the structure is circular, the cross section is circular, it is prudent to use cylindrical polar coordinate system to solve this problem. Okay. So, we will understand first the components of stresses in cylindrical polar coordinate system. Okay. Now, let us assume that this is Z, that is x and that is y of the cylinder, and the cross section is shown here, which is essentially in the xy plane. This x, this is y. Okay. Now, if I want to study a problem in cylindrical polar coordinate system, I have to say what is the component of stresses mean in cylindrical polar coordinate system. Okay. You know that in cylindrical polar coordinate system, you have to transform from x, y, z, E x, E y, E z basis to radial, circumferential and axial basis, okay, where E r is given by cos of theta E x plus sin theta E y. I will mark what theta E r E theta is shortly, minus sin theta E x plus cos theta E y, and E z in cylindrical coordinates would be same as E z in the Cartesian coordinate system. Okay. Now, this is y and that is x, that is x. Any point in here as coordinates given by the radial distance r from there to here, and this is the theta, the angular position of the point. Okay. Now, E r then is defined as the radial vector pointing along the radial direction, that is this is E r, and E theta is tangential to the circle that passes at that point E theta. Okay. That is, if I draw a circle with radius small r, E theta will be tangential to the circle at that location. For example, if I am looking at a point here, E r is the outward normal to the circle, which is E r, and E theta would be tangential to that circle E theta. Okay. So, now resolving E r into the basis E x and E y, you can see that you get this relationship that I have written here. It is just like taking component of E x, E y along E r, E theta, E z direction. Okay. Okay. So, that is E r, E theta. The point to note is the radial vector and circumferential vector in cylindrical polar coordinate system changes from point to point. Okay. this is called as the radial basis and this is called as circumferential or hoop basis. Okay, that is C theta is called as a circumferential or the hoop basis and ER is called as a radial basis. Okay. Now, to understand what different components of stresses, the 6 component of stresses in cylindrical polar coordinate mean, I have to section now to find out what the 6 components of stresses in cylindrical polar basis mean. Just like we drew a stress cube, now I have to draw a segment of a cylinder and show you those 6 components of stresses. Okay. So, let us do that next. Okay. So, this is a segment of a cylinder, okay, where ER, E theta, EZR, this is ER, this is E theta and this is EZ. Okay. Now, let us look at the positive oriented EZ phase. Okay. That is, I am looking at this, area, okay, this cut surface whose normal coincides with the positive oriented EZ normal. Okay. Now, what is this normal stress? This normal stress would be sigma ZZ, is also called as the axial stress. Okay. Now, next let us look at the tangential or circumferential basis. Okay. Let us look at the circumferential basis. Now, this is the cut surface for which E theta is positive, the circumferential basis is positive, okay, and hence this would be your sigma theta theta or your hoop or circumferential stress. Or the circumferential stress. Okay. Now, let us look at the positive surface whose normal coincides with the radial basis. That positive surface is this surface in here, that is the normal ER acting on this face coincides with the positive oriented radial basis, okay, and hence this stress is sigma RR or the radial stress. Okay. Okay. Now, correspondingly negative basis you will have this as sigma ZZ, you will have this as sigma theta theta and this would be a sigma RR on the respective other side of the cut surface. Okay. Now, we'll for completeness we will complete the shear stresses also. Okay. Now, what will this shear stress be? The normal to the cut surface is Z and the shear stress is acting along the theta direction. So, that will be sigma theta Z, okay, or to be precise sigma Z theta. I am not going to distinguish between theta Z and Z theta. Okay. Same thing here, this will be sigma theta Z, okay, and then this stress would be sigma RZ, okay, and the stress acting on this face would be sigma RZ. Okay. Now, we have seen 5 components, the remaining component is sigma R theta is the component that we have not seen till now, that would be in the radial basis it will act like this, that will be sigma r theta, okay, or in this phase it will act like this, sigma r theta on this positive phase is acting in the theta normal surface in the r direction. So, this is sigma r theta and this will also be sigma r theta, okay. That is the other component of the shear stress in there, okay. Now, having understood the components of the meaning of the components of stresses in cylindrical polar coordinates and the direction in which they act, now let us go ahead and see what is the gradient of displacement and divergence of sigma in cylindrical polar coordinates. I am not going to derive these equations, I am going to take it as given to you, okay. So, H, which is gradient of displacement field, where H is gradient of the displacement field, is given by dou u r by dou r, u r by r dou theta minus u theta by r, dou u r by dou z, dou u theta by dou r, dou u theta by r dou theta plus u r by r, dou u theta by dou z, r dou theta by dou z, okay. Similarly, the divergence of sigma in cylindrical polar coordinates is dou sigma r r by dou r plus dou sigma r theta by r dou theta plus dou sigma r z by dou z plus sigma r r minus sigma theta theta by r, dou sigma r theta by dou r plus dou sigma theta theta by r dou theta plus dou sigma theta z by dou z plus 2 times sigma r theta by r, r z by dou r plus dou sigma theta z by r dou theta plus dou sigma z z by dou z plus sigma r z by r, okay. Those are the expression for divergence of sigma and gradient of the displacement field, okay.